Okay, now we're going to put it all together that you've learned and try to make a weather forecast. You've learned a lot about the different variables that go into weather forecasting. You've learned a little more specifics about the mid-latitudes, about the global, about thunderstorms, and even about the tropical weather. But if you were trying to make a forecast for the weather in the next 5 to 7 days in Ohio, there is so much more that needs to go into that forecast to understand it. So let's take a look at what we can get here a little bit with this. So overall, for the world, there's something called the World Meteorological Organization. It's based out of Geneva, Switzerland. Under its auspices, shall say, each country has their own weather service. But through the World Meteorological Organization, all the countries cooperate. In other words, we get data from Iran or Iraq or wherever in the United States of their weather, because every country's weather affects every other country. So if you're going to have a good forecast for your country, you need every other country's weather. So that's what the World Meteorological Organization does. It coordinates that so that all 188 nations provide weather. Now, what do we do with this weather? Well, we want the best observation we can get to start. So we have what we call the global observing system. So you have the satellites. We've talked about the polar orbiting ones. They go around every few hours. And the geostationary, which stay over the same area. Both of them provide information about the atmosphere, the vertical structure of the atmosphere, parts of what's down on the ground that may influence the weather. Then you go out over the oceans and you wind up with a data buoy here, maybe a ship there. So you don't get a lot of data over the oceans. Now, over land, you can add aircraft, and you get that over the ocean some. But many aircraft are equipped now that you get observations as they take off and land, and even when they're flying. So you can actually see how the pressure changes, what the winds they experience, what the temperature is. It's very similar to an upper air station, like a radio sonde that we talked about earlier. Then there are surface observing, ASOS, even AWOS, which is another type of surface observing systems at smaller airports. They're automated. And finally, we have weather radar to get into this. All of that information still doesn't give you a complete picture of the atmosphere. So there's still holes. So we lose calculations, we use statistics to try to fill in these gaps, to try to get the best observation system we can, so that we can initialize all of our numerical models and all of our forecasts with the best observation of the current weather. When I was working, we used to grab all these observations we could, and literally every hour, many times we would go through and do our own local analysis, because you would pick up things that the computer generates you an analysis every hour with a whole bunch of information, but it misses things. So, being the forecasters, being human, we look for things and pick out things maybe that the computer missed or that we can spot to try to make a better forecast, to improve our forecast. There are 122 National Weather Service offices. Data buoys, you can see those here. Cooperative network is just a climate network. It's all volunteer. It's all over the United States, where they take a high and low temperature each day and a precipitation each day, all starting at 7 a.m. and through 7 a.m. every morning begins the new day. So by looking at this, we're developing a climate record for the United States. However, they're not always real useful in real time. Sometimes we can get the information from them, but not real fast. Radio sondes we've talked about before, and these are where the radio sondes go up. You can see there are really a lot of holes in the United States. If you look at Ohio, you have one radio sonde out in Wilmington, Ohio, and another one over in Pittsburgh. There's nothing in between. That's a lot of information that's missing there. AWIPS is an automated system that puts all forecast, all observations together in a way that a meteorologist can use. You look at it here, you can see there's 3 screens. It's been updated in the last several years, and it's still continually being updated. There's a deluge of information. If you're a meteorologist, you'll have 10, 15, 20 models looking at. You can have weather. You just saw where every one of these different equipment gives you weather information. So what do you do with this? We make short-range forecasts, which we consider basically 48-hour forecast or short range. Medium range is out through 7 days. So as a meteorologist and as the National Weather Service, we expect to be pretty darn accurate in the first 48 hours. Matter of fact, it's considered a bust on a forecast if I miss a temperature by more than 3 degrees in 24 hours. So that is a pretty accurate forecast because it's very hard to tell that 3 degrees. Now, if that 3 degrees was between 31 and 34, you might notice it. But overall, if that 33 degrees was between 71 and 74, I don't think you would ever notice that temperature change. 3 to 7 days, we try to pick very well. And then we have the long range, 6 to 10, 8 to 14, 30 days, 90 days, seasonal outlooks. And we have the 30 days, which literally go out 13 months. So there are numerous numerical models. I want to show you a few of those in a minute here. And we get an ensemble of these models too, even more confusing. So if this is how the forecasts have improved over the years, look at this in the Atlantic Basin. The error for the forecast of where the track is getting smaller and smaller. So in other words, if I tell you 120 hours out now, and this is even better now than it was in 2016 when this was done, your track error probably is less than 150 miles. And think about that, 24 hours out, 120 hours out. Now, if I'm down in the red, I'm less than 50 miles. That's a pretty good error, pretty small. Now, intensities, we're not doing as well. And that's where we're putting a lot of money and effort into it right now, improving the intensity forecast. The National Center for Environmental Prediction is based out of at Washington, D.C. And it's actually out of College Park, Maryland is the main hub of it now. But there are branches of it. And the forecast office makes the forecast for a local area. But say you want a specialized forecast. And while I'm at the forecast office, I may write a forecast for aircraft. But if I want to look at the whole country and be specialized to aircraft, as a broad sector, I'm looking to the Aviation Weather Center. And they're part of the National Center for Environmental Prediction. Storm Prediction Center down in Norman, Oklahoma. What they focus on is severe weather. They don't care about anything else. They care about severe weather, such as fire weather, severe storms, very heavy rain. And they coordinate then with the local forecast office to put out watches. They don't do the warnings, but they'll help put out watches and even talk to the forecast office to tell them about what area they think may be very dangerous. There are river forecast centers. We do river forecasts, meteorologists do. And you can see in Ohio, all of Ohio is under Wilmington, Ohio River Forecast Center. State College, that's part of the eastern United States. Each of these forecast water. They have to know how much water is coming into the area, hitting the ground, how much of that water is being absorbed by the ground, how much is running off into the river, how much flow is in those rivers already. And all of this to make a good forecast for exactly how high those rivers are going to be so we can tell you when it's going to flood. When is that Ohio River going to flood? Or your river, or those creeks by your house? We may not go down to the creek level, but the River Forecast Center it takes all that information to make major river forecasts. We have a marine forecast, Ocean Prediction Center. Their whole job is forecasting over the oceans. We have a space weather prediction, who actually forecasts the severity impacts on GPS signals and stuff, or aurora forecast. And then we talk about skills. Through the first 48 hours after that, skills begin to diminish fairly rapidly until you get out beyond 10 days, and I can pretty much flip a coin to whether it's going to be an accurate forecast or not. And right now, it used to be back in the 1990s, I could have told you that there were a lot of high-level executives in the National Weather Service and in the politics that were telling you that forecasts were always going to be all by computer in the next 10 years, and it didn't work out that way. Meteorologists still have a way, a knack, an intuition, experience with what happens. Like I can look at a weather pattern, I know others do it, and we can go back in time and remember when patterns like this have occurred before and what happened with the weather, and we can actually look at them and begin to understand what might be different about this pattern and how that might impact your weather. Long Range Climate Prediction Center. We talked about teleconnections, where you can actually look at one part of the globe and see there's a big low in a Rossby wave there. Well, how does that impact, say, over the United States if that was over Siberia or over Europe? And there are impacts from that. If you have one location, you can expect the weather and the pattern to kind of develop into a certain pattern based on that one thing. So that's a teleconnection. They deal with looking way away from where you are to see how your local weather may develop in the next 6 to 10 days. So we look at a short-term forecast for weather prediction based on observations at one location. Well, usually they're pretty generalized, and let's face it, most days are sunny. If I were to make a forecast and tell you it was going to rain at your house today, 30% of the time is all that it ever rains probably in your house. And it depends on the season. Maybe in the summer it's only 25%. Maybe in the winter it might go up to 40%. But think about it. If I'm telling you there's a 100% chance of rain, then I'm telling you statistically that it's way more likely it's going to rain today than what you would normally expect. And I know when I used to forecast, I had a bias towards fair weather, and almost all meteorologists do, because that is what is normally going to occur. So it's very hard to put in significant rain or very bad weather knowing that predominantly good weather is what's going to occur. There are private sectors. Obviously, a lot of the private sector now has got into meteorology as well, making their own forecast. And every information from the Weather Service is put out. We do watches and warnings. And a watch is basically telling you that weather may occur, not necessarily guaranteeing it. But if I put out a severe thunderstorm watch for your area, one's issued, we have in conditions that are capable of producing severe weather. If I put out a warning for a tornado warning for your house, then I'm either telling you that a tornado has touched down, or we anticipate a tornado touching down shortly. So there are blizzard warnings. There are numerous kinds of warnings and watches that the Weather Service puts out. I know of no private sector company that puts out a warning message right now because of the liability issues. All of these are disseminated through the local media, through NOAA Weather Radio, whatever. So I just wanted to show you a little bit. This is a current forecast, and all the models, all the observations, this is what they're looking at. You can see here there's a weak warm front moving through the northern part of Ohio, kind of discontinuous down there. There's frontologists that have taken place down in this area, probably, and weakened it out. There's a little bit of precipitation down in southern Texas. See how it was to move out in time? Now that low has moved along. We got the cold front, but it's still not even down into Ohio. Warm front now is along the eastern part of the United States in day 3. Cold front dipping down, but instead of coming in from the northwest like a lot of them do, kind of being pushed down from the northeast. And you can see here it's getting down towards my house a little bit. So let me just give you an example of models. You can see on this page every model basically that's available to the National Weather Service, and there are more than these. GFS is a global forecast systems model. It looks at the whole globe. And it just recently got updated. so that the vertical resolution went from 64 layers in the vertical to 127 layers in the vertical. And it's 13-kilometer resolution in the horizontal. So it's not real detailed. But if I go to a NAM with this North American mesoscale model, that has about 200 layers in the vertical, and its resolution I can get down to 1 kilometer. And we have the HRRR, which I'm getting down to 1/4 kilometer, and even more resolution in the vertical. But you can't run those. We don't have the computer system to run those out over the whole world. So we run them in smaller areas. And we have a storm ensemble forecast model, which can look at a whole bunch of different models at once. What we do literally, since we don't know the exact observation of what the weather actually is, we might create 20 different statistically possible scenarios of what the weather is, what the current weather conditions are, and then run the numerical model on each one of those 20. And maybe we'll go in and tweak some of the physics in that model as well, so that you wind up with, now, for example, the global ensemble forecast system, I believe, has over 50 members. And if you were to look at the European computer system, the last I heard, it had over 250 members. So they run the model 250 times just to look at what the current forecast is. And you can get to see errors that way, especially when you get out into the future. So if I were to look at the GFS mean spread, for example, and just look at North America, and we'll just take a look at 500 millibar winds, and I'm going to look at 96 hours out. There's a lot of error in this big wind out here. This is the mean, but this is telling me there's a lot of error in this very strong wind field out here. So you can go back here, actually look at, instead of this, we'll look at the spaghetti diagram for North America, and you'll find, let's look at the 500 millibar. And we'll look at 120 hours out, which is basically 5 days. That's a mess. You can see here on the left-hand side the number of different ensembles. We have 30 of them right here. And what I'm seeing is, a lot of the ensembles think there's a low trying to deform over the Midwest in 120 hours, and there's another low off the East Coast. But to tell you the truth, I have no clue where that low is. They're just telling me there's a big low up here. They give me a broad idea that a very strong jet is probably moving through here and across with a wave in the west and another wave up here to the north. But there's at least 2 instances where I have lows that are way down, well south. So this is a very confusing forecast. We'll have to see how it plays out this week. So this is just what I wanted to show you, just some ideas of the detail and the information. If I wanted to show you one last thing here, we can go back quickly. And instead of looking at the GFS, I'll just look at a high resolution model. So we'll go back to that quick. And we'll look at the HRRR. And we'll look in US North Central. There's not really much happening here today, but let's see if there's any snow, any simulated radar. And we'll just look at 1 hour out. Bang. And this actually simulates what the radar would be like. And you can actually see a few up in Canada, but not much around. So this is the high resolution, looking at the details here. So I hope you got something out of all this course and talking about forecasting. If you have any questions this week, please don't hesitate to ask.